So it's lecture 9. Okay, so lecture 9. Oh, okay. So today I want to do 3 things. So I want to wrap up our discussion of 2 important subspaces associated with the matrix, namely the column space and the null space of a matrix. Then I want to talk about, I want to show you a pretty surprisingly sort of effective application of some of the stuff we've learned in machine learning. And then finally, I'll do a review of what we've done for the exam, which, as you probably know, which is starting at 8 p.m. tomorrow, and we open for 36 hours. Okay, so that's the plan. So let me start by just briefly reviewing these 2 subspaces that we talked about last time. So let me just recall the definition. So given an M by N matrix A, so this is a matrix whose columns we'll write as A1 through AN. Oh, okay. Let me just get that glove again. I'm not sure why this is happening. Okay. So suppose you have an M by N matrix like this. We have these 2 subspaces associated with the matrix. We define the column space of A to be the span of the columns of A. So it's a very natural definition. And this is a subspace of Rm. And we defined the null space of A to be the set of solutions of the homogeneous equation AX equals 0. And that lives in Rn. We also actually discussed how to find a basis for these subspaces, right? So to find a basis, so there were different methods for these 2 different subspaces. So for the null space, it's quite straightforward. Well, you're looking for a basis of the set of solutions of AX equals 0, and that set of solutions is parameterized by the free variables after you compute the row echelon form. And it turns out if you just write that as a span, you get the basis. So you just express the solution set of AX equals 0 as a span parameterized by the free variables. And so one consequence of this algorithm is that, in particular, it tells you how many vectors there are in the basis, because the vectors in the basis are parameterized by correspond to the free variables. So one consequence of this is that the dimension of the null space of a matrix is equal to the number of free variables. So this is some fact that we observed last time. And then there's the other subspace is the column space. There's a method for finding a basis for that, also related to row reduction, but it's different. And computationally, it's actually simpler. It's just compute the row echelon form R of a row equivalent to A. And then the basis is just, you just choose the columns of A corresponding to the pivot columns of R, corresponding to pivot variables. And so we gave an explanation for why this works at the end of the last lecture. But I mean, the algorithm is quite simple. And one consequence of this is that the size of the basis, remember, the dimension of a subspace is the number of elements in a basis. The size of the basis is just equal to the number of pivot variables. So the dimension of the column space of A is equal to the number of pivot variables. Okay, and this, this reveals that there's actually a close relationship between these two subspaces, right? And well, the reason there's a close relationship is that the number of free variables plus the number of pivot variables in an m by n matrix is just equal to the number of columns, which is n. Right? So for any m by n matrix, the sum of these two quantities is just the total number of variables, which is n. So this is a very important fact, which we'll talk a lot more about after the midterm. But I mean, well, it comes in handy even for things we've done already. So the consequence is that for any m by n matrix A, the dimension of the null space of A plus the dimension of the column space is always equal to n. And so this is a famous, sort of important result. This is called the rank nullity theorem. These numbers have names. This is called the nullity of A, and this is called the rank of A. The rank is just the number of pivots. Okay. So this is called the rank nullity theorem. And what it's saying is that these subspaces have a very close relationship, that if one of them is big, the other one has to be small because the sum is always equal to n, right? So it says if one is big, the other must be small, and vice versa. And this actually implies a lot of the statements we've looked at earlier. For example, it implies the Goldilocks theorem, right? Okay. So what are some connections? So let's recall that the linear transformation corresponding to A, which goes from Rn to Rm, is onto if and only if. Well, if and only if its range is equal to Rm, but then the range of TA is equal to the column space of A. And so this is if and only if column space of A is equal to Rm. And the same linear transformation is one-to-one if and only if the null space of A is equal to the trivial subspace. Right? If and only if dx equals 0 has only the trivial solution. So this is how we connect column space and null space to concepts we learned about before, namely being onto and one-to-one for the linear transformation. And I guess I'll just mention that in the special case m equals n, then this kind of implies the Goldilocks theorem. So why is that? Well, well, TA is onto if and only if the dimension of the column space of A is equal to n. Equal to n m, which is equal to n. So I used m equals n here. And that's now by the rank nullity theorem. This is true if and only if the dimension of the null space is equal to 0, right? Because they have to add up to n. But then this is true if and only if TA is 1-to-1. So this rank nullity theorem, you can see it as a generalization of this Goldilocks phenomenon to all general matrices. It said if one is big, then the other has to be small. So any questions about this statement or anything on this slide or the previous slide? You can just unmute and ask.
About the line saying onto is equal to the column space equals Rm.
Yep.
Isn't the column space definition is equal, like, I think column space equals to Rm is the definition?
No.
For the column space?
It's not. So the column space, if you go back to the previous slide, is the span of the columns of A, right?
Mm-hmm.
So it's contained in Rm. It's a subspace of Rm, but it's not equal to Rm in general, right? Saying it's a subspace. The column space of A does not have to be equal to Rm. What this is saying is that it's equal to Rm if and only if the linear transformation is onto.
Oh, okay.
Yep.
Okay, thank you.
Any other question?
Professor, I missed what the 3 dots meant on the previous slide.
Oh, the 3 dots just mean therefore. Sorry. So these are just notation, which means therefore.
Great, thank you.
Any other question?
Yeah, I have a question.
Mm-hmm.
When null A is equal to the 0 vector, that means that the matrix is 1-to-1, right?
Correct. When null A is equal to 0 vector, not the matrix is 1-to-1, the linear transformation is 1-to-1.
Oh, okay.
Yeah.
But then when it's just equal to the 0 vector, does it mean that the dimensions of A is 0?
Yes. So remember, the dimension is the size of a basis, and the 0 subspace actually doesn't have a basis. So I mentioned this in the last lecture, the dimension of the trivial subspace is defined to be 0.
Okay.
Any other question?
Wait, does that mean that the dimension of A is 0 or the dimension of null A is 0?
The dimension of the null space of A is 0.
Okay.
So here I'm just saying the dimension of the 0 subspace is defined to be 0. And being 1-to-1, TA is 1-to-1 if and only if the null space of A is the 0 subspace.
And that's because only when the null space is equal to the 0 vector, that implies that there's a pivot in every column.
Yeah. Okay. So yes.
Okay. If there's like quote unquote proof questions on the exam, can we just straight up say like because of the so and so theorem?
Yeah, so I'll talk about that later during the review session, but yes, basically. I'll talk about how you can write about proofs later. Any more questions about this? We'll be revisiting this a lot after the midterm as well. So the word rank, by the way, which was on some of the practice exams, it just means dimension of the column space, and it just means number of pivots. It's a very concrete quantity ultimately. Okay, so somebody asked during office hours, why are we studying these subspaces? And I want to give a little bit of geometric intuition for this. So why these subspaces? And I just want to remind you of something you probably learned in high school, which is that there are two different descriptions of a line in 2 dimensions, right? So recall 2 ways to describe a line L in R2, a line through the origin. So the first way is to write it as the solution set of an equation, right? So as solution set of an equation. So that means you write this line L as, it's a set of x1, x2, so that some equation is satisfied, right? So let's just write it like this. So this is y equals mx plus b, but b is 0. And so this is just y equals mx, right? So that's one way of writing. So the geometric object that's being considered here in both cases is just a line through the origin. Okay, it's not through the origin. Okay, but there's another way to describe it, which you certainly you learned if you took Math 53, but maybe you learned it in high school as well, which is different. So, which is in parametric form. So parametric form means you choose some direction on this line, which is a vector. Let's call this vector v, and then you say, well, it's all points you can reach by moving along that direction, right? Set of all x in R2 such that, so this means such that, people have been asking again in office hours, so let me just remind you, such that x is equal to some multiple of v, where t is some real parameter. Okay. Now this is a description, from the outside. I mean, that's one intuitively how I think about it. It's telling you what constraints you have to satisfy to be in the subspace. And parametric form is a description from the inside. These are in quotes, so I'm not going to mathematically rigorously define them. But now, column space and null space are just the higher dimensional generalization of this, right? This is the null space of a very simple matrix, this matrix. And this is the column space of a very simple matrix, namely just the matrix that has the vector v in its column. And so what we've done here is just generalized these simple descriptions to higher dimensions. Okay, that's why we care about column. I mean, that's why column space and null space are very natural geometrically. So any questions about that? So I told you in the beginning that.
Could you?
Yeah.
Oh, sorry. Could you explain again what you mean by from the outside and from the inside?
Well, I just mean that the left-hand equation is telling you that in order to be on the line, you have to satisfy some constraints. So it's in some ways it's telling you what's not on the line. I mean, this is just my intuition for it. It's telling you, in order to be on the line, you have to satisfy this rule, right?
Yeah.
The parametric form has a very different feeling. It's saying, hey, here's a vector, and just move around as much as you want in this vector, and you'll get the line. So it's telling you how to draw out the line from the inside, whereas the first one is telling you start with R2, and then delete all the points that don't satisfy the equation, and then you'll get the line.
Okay.
Yeah. Any other? Okay, so let me now, so that's all I want to say about this for now. Let me now quickly show you an application of this, or an application of just the language that we've learned, right? We've learned about vectors, matrices, et cetera, et cetera. We'll see much more sophisticated applications later, but I'll show you one already that's kind of cool, I think. So let's Okay, so here's a cartoon, which I like, which is partly accurate, from the comic XKCD. So it's a picture of machine learning, at least right now. And well, okay, you can read the comic, but you can see some things in this pile that are there are some quantities we've seen, like matrices, although there's a lambda 1 in there. We haven't seen that yet. So so if you haven't done machine learning, you may not, I mean, you may not really know what this means. So let me now show you a really simple machine learning system you can make out of in even linear algebra we've learned so far, which is actually quite influential. So so let's see. Okay, so this is an idea which came out of a paper, this paper, which at this point has 20,000 citations, which is a paper that came out of Google in 2013, I guess. Okay. So so what does this paper do? So this paper addresses the following type of question. So there's a very high level question you can ask, which is, you know, what are the meanings of words? So like, let's say words in the English language. What does it mean to have a meaning, et cetera, et cetera? So this is kind of a philosophy question. But you know, you can ask a much more modest question. You can ask an operational question rather than a semantic question, which is, can a computer understand the meaning of words? The meanings of words. I mean, this is still in some sense kind of underspecified because we don't know what the meanings of words are. So you can pick a specific task, and in natural language processing, there are several tasks that you can try to get a computer to do to check if it has some implicit understanding of the meanings of words. And so one question you can ask is, can a computer solve analogies? So analogies are these things that you probably saw in the SAT. So for example, here's a simple analogy. Woman is to man, as queen is to what? So this is the analogy considered in this Google paper that I cited, or one of the analogies in the introduction. And so how would you program a computer to, let's say, solve SAT questions? That's a valid thing to try to get it to do. And then you can even measure how well it does. So it seems that to solve an analogy, you need to understand the meanings of words. And so what are meanings? So here's an operational definition that was proposed by Firth, who I believe was a linguist in 1957. And what he said is that you shall know a word by the company it keeps. Okay, so I mean, this is, I guess, a somewhat this is just he's just saying that, okay, the meanings of words are defined by their relationships with other words. So this is not a really new idea in linguistics. But this actually led to the key idea of this paper. And the idea is you can encode the meaning of a word sorry, so you can, not the meaning of a word, you can encode a word's company. So the nice thing about the definition is, so the word, it reduces meaning to this other concept, which is company. So encode the company of a word as a vector. Okay, so what do I mean by that? So so here are the steps in this protocol, or here are the steps in this approach. So step one is to choose a longish list of commonly used English words, the words that you care about, that you think are going to appear in this analogy. So select a list of commonly used English words. So how big should this list be? Well, the English language has a lot of words. I guess they say to be fluent, you need to know about 10,000 words. So let's choose about 10,000 words, and let's call this list W1, W2, W3, all the way up to W capital N. So this is just literally a list of English words. So for example, the list might start with, I don't know, dog, apple, data, they, ... Okay, there's just some list of, it's just make this list of words. Okay, so that's some sort of a list of the words in the English language that we care about. And now we need to associate every word with a meaning, and we've decided that the meaning is going to be somehow encoded as the words that are its company. So what do we mean by that? So we're going to, step two, this is where the machine learning happens. We're going to find a real document. So that means like a document written by humans. So for our example, I guess why not be self-referential? We'll just use the Google document itself. Okay. And now here's an answer from Google. Oh my God. So my phone, okay, this is really creepy. My phone thought I was talking to it, but anyway. So then map every word in this list to a vector. I'll underline it to show you that it's a vector. In the following manner. So this vector has n entries. That was the total number of words, right? So every word has a vector, and each vector has itself n entries. And the jth entry for the ith word is going to be the number of times wj appeared in the same sentence as wi in this document. Okay, so for example, let's go back to look at our document. So we had this paper. Okay, so this is a document, it's an English document. And let's say we care about the word, data. Here's the definition of word. A single distinct meaning element of speech or writing, used with others, or sometimes alone, to form a sentence and typically shown with a space on either side when written or printed. Okay. I should probably turn off the phone, but anyway. So let's say we're interested in the word, data. Okay, so that's some word. Let's just say it's the first word. Or actually in our list, it was the third word. So W3 is the word data. And now what we're going to do is we're going to look at, we're going to look through all the sentences in this document. And the vector corresponding to this word is going to have an entry per word in our list, right? Like the first entry is going to be for dog. The second one is going to be for apple. The third one is going to be for data. And then maybe there are some other words in here like complex, maybe the word set. And what we're going to do is we're going to go through the document and see which words occur with the word data in a sentence. So the word sets occurs here. Okay, it's going to take me some time to do this manually, but let's see, the word data appeared here. The word complex appeared in here. The word data appeared again. You know, okay, it would take me a while to obviously go through this document, but I'm going to keep doing this. Okay. Okay, so if you keep doing this, so the word data and dog and apple probably don't appear together. I don't know if we're going to count it if it appears for itself, but it appeared, let's say, once with the word complex. I think if you go through this page, it appears twice with the word sets, et cetera, et cetera. Okay. So I've turned a word into a vector just by counting co-occurrence frequencies with other words. So any questions about this? It's not a complicated function. So, okay, so we're going to do that. And now we have n vectors in Rn, right? Where n is about 10,000. Okay, so we've turned words into vectors. That's why it's called word to vec. And now we're going to do the most naive thing possible, which is we're going to try to just use vector arithmetic to solve analogies. So any questions so far about how we created these vectors?
What would
Okay.
WJ stand for?
Sorry, can you say it again?
What does the WJ stand for? Let's say in this example, the data example.
Oh, so the WJ is the another word, right? So WI is a word. WJ is another word. So for example, you know, the vector corresponding to the word data is a 10,000 length vector whose entries are indexed by the entire set of words itself, right? So these are the WJs. I mean, these are WJs, right? And so I've said that, you know, in the position complex, I put a 1 because in my document, data and complex appeared in one sentence together. Does that answer the question?
Yeah.
Yeah. Okay. So now I'm going to use this to solve analogies. So so step 3 is to use vector arithmetic to solve analogies. So what do I mean by that? So this was my original analogy, right? Queen is to something. Okay, so what is that something going to be? So these are now vectors living in some Rn, right? So, you know, maybe there's a vector for, so there's a vector here for man. There's a vector here for, sorry, for woman. And then there's a vector, I suppose, for queen. And so I'm going to do the most naive thing possible. I'm going to imagine that the relationship between words is represented by their difference. Oh, sorry. I was interested in the relationship between, I guess, woman and man rather than woman and queen. So I'm interested in woman as to man. And so I'm just going to imagine that the relationship between these vectors is another vector, which is the difference. So let's say it's man minus woman. And if I believe that queen should have the same relationship to whatever the solution of this analogy is, it should just be queen plus the same difference. And so the question is there a vector here? Is there actually a vector? So remember, I've plotted 10,000 vectors somewhere in the vector space. Is there a vector here? And so what the computer is going to do is it's literally going to output queen is to queen minus woman plus man. Okay, so that's, you can do that. Those are 3 vectors in Rn. And it turns out if you do that arithmetic, you actually turn out to get the vector for king. So if you look around in this space, if you just do this on a computer, the vector you get is actually king. Okay, so this, I found this kind of surprising because it's incredibly naive, right? It's, you just write, you encode words as lists of other words, and then you just do subtraction to measure relationships. But this actually seems to work. So for example, you can, I mean, there's a, there are many websites that you can run this demo. So of course, okay, in the Google paper, they do some fancier things, but even this super basic version actually works surprisingly well. So here's a website that I'll put a link to. So this is trained on Google News, which is some large set of words. And okay, you can plug in this analogy. And sorry, why isn't? Yeah, okay. So it outputs that these are the top 2 choices. But now you can run this on whatever, right? Like, I don't know, Japan is to Iran, as USA is to yeah, I don't know. I mean, you can type in whatever analogies you want, and this is literally just doing some very basic vector arithmetic, and it's giving answers that are not totally garbage. So anyway, I mean, later on in the course, we'll look at more sophisticated, make this better and so on. But the summary of this is it just kind of explains why vectors are used in machine learning. Representing data as vectors is somehow the
Professor, we can't hear you suddenly.
Can you hear me now?
Yeah.
Sorry. Yeah. Okay. So the summary is that the pairwise relationships between words are reflected in the differences between the corresponding vectors. So literally differences in sense of subtraction. And I mean, later in the course, we'll see how to reduce. So right now, this is happening in R to the 10,000, right? So this is also meant to be an example of why would you think about high dimensions. Often high dimensions just means a representation of some, some space of, well, features is what it's called in data science. And so high dimensional spaces appear very naturally in, for example, in statistics and in data science. So that was one app. That was the application. Any questions about that? You don't have to know this for the exam. Some people asked. It's mostly just there to connect it to some other things you might know or care about. So I should mention that, yeah, last time I taught the course, like some people went and implemented this and they tweaked it and they actually got really good results out of it. So if you're into programming, as you can see, it's not very difficult to program. Okay. So now I want to move on to the review section of the lecture. Any questions about this before we proceed? Okay.
So do they like find synonyms of words by just looking at which word has a similar vector?
Yeah. So that literally that website. So we will discuss what it means for vectors to be near each other later in the course, but you can also find synonyms just by taking a vector and looking at the cloud of vectors near it. I mean, I might as well, okay, since you asked, I might as well show you what these word embeddings look like. So
Linear algebra is basically
so let's see here.
not code. It's basically the backbone for computer.
Okay, so here's a low dimensional image of one of these embeddings. We'll discuss later in the course. So this is an R200. We'll discuss how to bring it down to R3 later. We'll do that in chapter 7. But these are now vectors in R3, and they all correspond to words. Now in R3 is kind of very low, so a lot of words are getting collapsed together, but still like Bach and orchestra and ear and these things are genres apparently are close together. So you can see it's not totally garbage. And indeed, you can make a pretty good thesaurus out of this. And I think they, using a pretty simple word to vec embedding trained on, I don't know, some standard literature, you can even get a pretty good SAT score. So I don't think this is really proof that computers are intelligent, but it's pretty stunning that you can do so well. Okay, so let me now briefly review, try to give you a big picture of a lot of new definitions, and sometimes you can get lost. Okay, so the third thing I want to do is briefly review. And what I'm going to do is I'm going to write down all the different types of objects that we looked at and how to translate between the types of objects and also between the different types of statements about those objects. So okay, so the basic object we looked at is vectors. Which is just an array of numbers that looks like this. And then we looked at, in the different weeks of the course, we looked at different types of objects associated with vectors. So in the first week, we looked at augmented matrices, otherwise known as linear systems. So we looked at something that looks like this. Okay, I guess I have to put on that glove again. Or maybe I'll just write it in vector notation. And then in the second week, we looked at sets of vectors. So you could look at a set of n vectors in Rm. And then in the third week, we looked at matrix and the associated. So a matrix of vectors was now you just place the vectors in the columns. And then finally in week 3, we looked at linear transformations. So this is now a function going from Rn to Rm. And all these objects, there are ways of converting between them, in a sense, right? So every set of vectors, so I'll use a different font for color for this. Every set of vectors corresponds to a matrix just by putting it in the columns. And every matrix corresponds to a set of vectors by taking out the columns. And the way you do that is by doing matrix multiplication. Okay. Similarly, if you have a matrix that defines a linear transformation just by dA of x equals ax. And if you have a linear transformation that comes from a matrix by taking the standard matrix, which is you just apply t to the standard basis vectors. And of course, okay, I mean, the augmented matrix is just, the augmented matrix is actually something that concerns not just a set of vectors or a matrix or linear transformation, but it's what you get when you ask the basic existence question associated with this, which is, so for vectors, the basic existence question is a given vector a linear combination of some other vectors? So is some b equal to x1, a1, all the way up to xn, an, for some coefficients x1 through xn. Okay, so maybe I'll draw lines between these things just to keep them separate. Okay, and then that same question translates to, in matrix notation, is just a linear system, right? It's just does ax equal b for some x? So okay, I don't want to keep writing for some, so I'll just write it like this: b is equal to this. Okay. And again, for linear transformations, you have a corresponding question: is TA of x equal to b? Okay, or maybe I shouldn't even write it as a question. Just write this statement, right? So you have this relationship. So in the vector world, that's a linear. It's saying that b is a linear combination of a1 through an. In the matrix world, it's saying a times x is equal to b. In the linear transformation world, it's saying TA of x equals b. So the linear transformation TA maps x to b. And when you ask the question of do such x exist, you get this linear system. You get the augmented matrix on the left, right? So all these are related. So it's very important to, one thing I've noticed in office hours is people often ask something like, is the matrix linearly independent? That doesn't actually make sense. Each of these types of objects has its own set of adjectives that can be ascribed to it. And it's important to keep these columns separate. Okay, so then let's see. So okay, so this is called a linear system, right? So this is what I'm calling a linear system. And now about each one of these things, you can ask some basic existence and uniqueness questions. So the basic existence question for a set of, well, I mean, okay, you can ask, so you can ask a question about one vector, which is b in the span of a1 through an? Is there an x so that ax equals b? Is there an x so that t of x equals b? Or you can ask more global questions. So here you can ask, so there's an existence question. You can ask, is the span of these vectors equal to Rm? And that corresponds to an existence question here in terms of the linear system. Really, this is asking, does ax equal b have at least one solution? For every b in Rm. And in the linear transformation world, this is just saying that TA is onto. And then you have a uniqueness question, or you have a list of uniqueness questions. And here the uniqueness question for a set of vectors is, are these linearly independent? And this statement corresponds to a uniqueness question for the linear system. Ax equals b has at most one solution for every b in Rm. And this corresponds to TA is 1-to-1. Okay, and then what is the point of setting up this correspondence? Well, I mean, according to me, so first of all of these kinds of objects are interesting. They appear in different contexts. But really, one way to think about it is that the objects to the right are more abstract than those to the left. And these equivalences allow you to reason about the things to the right by reasoning about the things to the left, namely augmented matrices are very concrete, right? So the workhorse of this course is in augmented matrices, you have this algorithm called row reduction. And you have pivots. And you have, pivot variables and free variables. And then the existence and uniqueness questions in this language are extremely simple, right? This is existence is just pivot in every row. And uniqueness corresponds to having a pivot in every column. Okay, so I mean, the whole point of building these equivalences is to be able to traverse between them, is to move around in this diagram. And okay, finally, I should mention the most recent thing we learned, which is subspaces. So I'll just draw it here. We learned about subspaces, H of Rn. And we learned about two important subspaces associated with a matrix, right? So we learned about, one way to get so there are two important subspaces associated with every matrix. These are the column space and the null space. And then we learned about a basis for a subspace. And you can think of, and to figure out if something's a basis, you need to answer some other existence or uniqueness questions. But they're actually the same as the existence or uniqueness questions below. They're just restricted to H, right? Okay, so this is sort of a one-slide summary of all the types of objects we learned, what the relations are between them, how to convert between them, what the existence and uniqueness questions are for them, how to convert between those, and ultimately how to answer everything using row reduction. Because in the end, row reduction, this is an algorithm, right? Okay, so that's, I don't know. So the point of this is not for you to memorize this. This is my representation of all the different things we learned in the course. I encourage you to make your own. So as written in the instructions for the final for the midterm exam, you have to submit with the midterm exam a cheat sheet that you make. And I encourage you to make your own mind map of all the different concepts appearing in the course. That'll be useful in solving the exam. And as I'll show in a moment, having a high-level overview like this can really help you solve questions in the course, because most of the questions involve moving from one part of this diagram to some other part by following these little equivalences. Okay. And
Professor?
Yep.
Do you mind if I ask for you to re-explain what's in blue?
What's in blue? Oh yeah. So what's in blue is how to convert objects of one type to objects of another type. Right?
So for the right-hand side, where you do the arrow of standard matrix and transformation of x to ax, can you explain more about that?
Yeah. So the arrow going from matrix to linear transformation is saying if I have an m by n matrix. So in all these things, A is an m by n matrix, right? So let's write that down. So A is, well, okay, A is m by n. And these blue arrows are saying that given a matrix, there's a corresponding linear transformation defined by TA of x equals AX. It goes from Rn to Rm. And so the blue arrow is just telling you how to turn a matrix into a linear transformation. And the backward arrow is telling you how to find given a linear transformation, how to find a matrix that implements a linear transformation. Does that answer the question?
Yes.
Because see, on the bottom there are some statements, right? Existence and uniqueness questions. So it says TA is onto if and only if AX equals B has at least one solution. Well, if I want to convert a statement about TA into a statement about A, I need to know how to I need to know which A I want to be looking at, right? That's what the blue arrows are telling you.
Okay, yes. Thank you.
Okay.
So like with this and throughout like the notes and whatnot, there's been a lot of like summaries, I guess, where we're doing the where like we're just drawing a bunch of equivalences and whatnot. So like on the exam, for example, can we just kind of use those equivalences or like?
Yeah, you just write those equivalences down.
Okay.
So let me put it this way. Well, I'll work out a problem in a moment to give a clear idea of what I expect on the exam. But
right.
Yeah.
Because it just feels like I don't know if cheap is the right word, but like I could imagine like doing a question where it's like you literally just write down the equivalence and like I don't know, it just feels like it's done already.
Yeah. So I'll say a bit more about why we're doing this in the broader context of math a little later as well. But it may seem cheap. After all, we're doing a lot of small things that each appear to be trivial, but when you combine them all together, you reach some surprising conclusions, right? Like our computation last time of why how to compute the column, the basis for the column space, right? That combined a lot of these little facts in a kind of interesting way to reach a not obvious conclusion.
Okay.
So yeah, I'll say a bit more about that in a moment. But
okay, thank you.
But okay, so what do I want to say about what to learn for the exam? Okay, so let's say things to learn. So the first thing you need to learn is the definitions. So you need to ideally memorize the definitions, because without the definitions, I mean, without the definitions, the questions don't even have a clear meaning. So this is like knowing the vocabulary in a language. The second thing you need to learn, and you need to be aware of throughout, is the different types of objects. And you should think of this as maybe part of the grammar of this new language that we're learning. So in this diagram that's drawn here, there are 4 types of objects, right? There are augmented matrices, sets of vectors, matrices, and linear transformations. And each of them has its own properties. And you have to be very careful not to confuse these types. Otherwise, you write sentences that don't make sense. So this is actually helpful in, I mean, it may seem like a constraint, but it's actually helpful in making sure that what you're talking about is actually meaningful. So in particular, always write down the dimensions. Any matrix you write down, always write down its dimensions. And then the third thing you need to learn is the theorems and connections between the definitions. And this is really what the meaning of linear algebra so far is. It's that we've defined all these words and they're all related in this very sort of tight-knit way, right? Like in the beginning of the term, you didn't know most of the words on the slide. And really what the meaning of this language is this web of connections between these words. Now, so how should you learn this? So the first thing that I said is memorize the definitions. And for each definition, come up with, let's say, 2 examples and 2 non-examples. Two examples and 2 non-examples. Okay, so for example, let's say the definition is onto. Okay, so first you should be able to write down the definition. So A linear transformation is onto if, so okay, so T going from Rn to Rm is onto if, okay, so you need to exactly be able to write down what it is, right? If for every B in Rm, T of X equals B has at least one solution. Okay, so knowing this definition means you also need to know all of the sub definitions. Okay, so one thing I've noticed talking to people is that even if you remember this, you need to know exactly what this means. You need to know what this quantifier means. You need to know what domain and codomain mean, right? So be able to know a definition means to know all of the definitions that it refers to. Okay. So first, so know all definitions of, know the definitions of all words appearing in the definition. It's a little bit like, I guess, our word to vec thing. And then know some examples, right? So what are two examples? What's an, just, you know, so first of all, okay, onto applies to linear transformations, right? So here's an example of a linear transformation that's onto, the rotation one. So this is an example. I'll just write one example for now. And now what's a non-example? Well, you know, it can be whatever, but I really encourage you to explore the space of examples. This is one new thing in this course that you may not have done before. You know, yeah, so it's to have a library of examples. That's kind of how you build intuition. So non-example is, I don't know, maybe the linear transformation TA for A equals, let's say this, right? That's not onto. So for every definition, be able to come up with two examples and two non-examples. Then ask how it relates to other concepts. So by that, I mean, go back to this picture or whatever version of this you make, right? So onto is appearing here on the left. And some relations are spelled out, right? Like onto is if and only if the span is equal to Rm, et cetera, right? But there are many connections that are not spelled out, right? Like you know, like you can now ask, what is the relationship between onto and you know, something that's, well, what's the relationship between linear onto and linear independence? How does being onto relate to the process of row reduction? You know, if I have an onto linear transformation, I don't know, you know, just make up, you know, what does it say about M and N, right? The dimensions of the domain and codomain, et cetera, et cetera. So, you know, ask yourself questions, I think, is a good way to think about this. Because while many connections are spelled out here, these are not all the connections. There are other ones that I'll ask you about. I'll show you a concrete example in a moment. Third thing I encourage for studying is to explain what you learned to someone. Okay, the exam collaboration is not allowed, but while studying, I think the best way to really know that you understand a definition or concept is to explain it to somebody or to ask another person questions. I mean, I think this is part of why I love teaching, because I actually feel like I understand linear algebra better after teaching, even though I've been doing it for so long. So these are some ideas, and of course, okay, do the practice midterms, et cetera, that I sent in the email. So now this has been a bit of an abstract discussion. Let me show you an example of a question, of a, you know, a slightly maybe not so easy question, and how knowing these definitions, types, and examples will help you answer this question. So let me give you an example question. So the question is this true or false? The following statement. If T going from Rn to Rm is onto and the span of some set of vectors v1 through vk is equal is equal to Rn, then the span of T of v1 through T of vk is equal to Rm. Okay, this is a true false question that I think maybe is on one of the practice midterms. So let's just let that sink in for a moment. Any questions about the question? Okay, so now I'm going to, so one thing that, a lot of people ask me in office hours is, well, if I'm stuck, then how do I get started? Right. So this seems like a lot to, digest in one moment, and it's really not clear how to start, right? So the first thing for how to start is to write down all the definitions. And in a true-false question, I separate the hypotheses from the conclusions, right? So this is an if-then statement, right? So if these two things happen, then this happens, right? That's what it's saying. So first, examine the logical structure of the statement, right? So if-then means whenever the first thing, whenever T is a linear transformation and V is a set of vectors satisfying the first thing, then the second statement has to be true. So now let's just write down all the definitions. So on the left-hand side, we'll write the hypotheses. And the right-hand side, we'll write the conclusions. And again, a common, really this course may be your first entry point into, math where there's a bit of logical subtlety and you can make mistakes in the logic. So remember, if you have an if-then statement, it's important to know what you're assuming and what the conclusion is supposed to be. So what are the hypotheses? Well, let's circle all the words, right? So onto is a word. Spanning is a word. It's a definition. This is a linear transformation. I need to know what that means. This is another span. Okay. So there are 4 words that I really have to know the meanings of. Otherwise, there's no way for me to know the meaning of the sentence. So let's write down all the definitions, right? What's the definition? So T is linear. That means it preserves linear transformations. Or maybe I'll write that at the end. So what does it mean for T to be onto? Well, okay, it's that for every B in R M, dx equals B has a solution. Okay. What does it mean for the span to be Rn? Well, just unpack the definition, right? Well, what does it mean? It means that for every, let's give it a different name, x in Rn, x can be written as a linear combination of the VIs. So that means x is equal to C1, V1, plus all the way up to CK, VK, for some coefficient C1 through CK. Okay, what does it mean for T to be linear? Well, it means that it maps linear combinations. It preserves linear combinations, right? And this is for every for every, C1 through Ck, right? So in every statement, it's important to, the other thing that's new in the course, which I think many people are having trouble with, is keep track of the quantifiers. This is for every X something happens. This is for every B something happens. This is X equal to this for some C. This property holds for every C. So keep track of quantifiers. Quantifiers just means for which values is the statement true. Okay, so we've now written down all the definitions that appear in the hypothesis. Now let's write down all the definitions that appear in the conclusion. Sorry, has a solution. Okay, yeah. So again, to be extra precise, let's make it has at least one solution, right? People are having a discussion in the chat about is it exactly one or at least one. It means at least one. Okay, now the conclusion we want to reach is that the span of these vectors is equal to Rm. And that, let's just unpack it. That's saying that for every B in Rm, there is a linear combination. So B is in the span of TV1 through TVK. There are C1 through CK such that C1 T of V1 plus C2 T of V2 okay. Okay, so that's step one, write all the definitions. Now, the nice thing is once you write the definitions, that will actually kind of give you some ideas for what to do. Okay. So remember, you want to get from the hypotheses to the conclusions, right? To the conclusion. At least if it's true, there should be a way to get from the left side to the right side. So now the benefit of writing the definitions is it gives names to things, right? It turns into into a statement about some B and X and some C1 through CK and so on, right? So now can you combine these statements on the left to get the statement on the right? Well, so I need to show that for every B, there's a linear combination like this, right? So the picture is something like there's R, also draw cartoons, it doesn't hurt, right? There's a B sitting over here, and I need to show inside Rn here, there's some set of vectors V1 through Vk that spans Rn, and I need to show that T of those vectors spans B, right?
You can start with the first definition for onto, and then replace X with the definition of span, and then use the definition of linearity to get the final result.
Yeah, okay. So you gave the whole solution, but the point is once you write all the definitions, there are only 4 pieces of information on the table. One of them is my conclusion. So there are only 3 pieces of information. And I just have to figure out how to combine them. So if I use the first fact, then I know that B has to come from some X, right? Tx equal B has a solution. So that's the first fact. The second fact is that this X is in the span of V1 through Vk, right? So I know that this X is equal to C1 V1 plus all the way up to CK Vk. That's by the second fact. And then the third fact is that linearity preserves a linear combination. So now if I literally write these 3 facts in this order, I'm actually done, right? I now have that for every B, I can find an X, so the Tx equals B, then I can expand that X as a linear combination of the vectors. And then by linearity, I have T of X equals B equals this. And this is what I wanted, right? This is the conclusion. So yes, it's true. Now, if this hadn't worked out, then what would you do?
Circle false.
No, you wouldn't circle false. You would go through your library of examples. So just so remember, if a proof doesn't work, that doesn't mean the statement is false. It just means that proof didn't work. So step 2 is try to combine hypothesis to get the conclusion. And then if that doesn't work, then go through your library of examples to try to find a counterexample. If that doesn't work, go back to step 2. So math is like an iterative process, at least for me in my research. I don't, the whole point is you don't know if statements are true or false, right? So you try to prove them. If it doesn't work, you try to find a counterexample. If that doesn't work, then usually you learn something in the process. So step 3, try to find a counterexample. And then step 4 is then if this doesn't work, alternate steps 2 and 3. Until one of them works. So creativity is required in this, okay? And that's kind of why it's interesting. But really all you're doing in these steps is you're moving around this map, right? Like each of these steps was, invoking some definition and combining it with other definitions. So this is my advice for how to approach problems. Write down all the definitions. First step for any problem is write down all the definitions. It will tell you how to solve the problem. Okay, so about proofs, it's enough to draw, diagrams with, arrows between them, as I did in class. Okay, so I'm not expecting some formal prose to be written here. I'm just expecting these arrows are basically if-then statements, right? And I'm just so this really just corresponds to moving around in this web of connections, right? So these corresponds to moving around in the web of if-then statements. And really, I mean, this is a valid definition of math, right? I mean, I don't know, I think Bertrand Russell might have said this. What's the definition of math? Well, math is a collection of all if-then statements. I mean, there are many definitions of math, but this is a reasonable one. And that's why definitions are so important, because if you don't understand the definitions, you don't even understand the if, for starters. So that's all I want to say about the exam. So good luck. Yeah, I'll send a few more guidelines about the exam closer to the date, but there's no class on Thursday either. So that's it.
Professor, can you go back to the page where you wrote the true and false again?
Yeah.
Super good.
Thank you, Professor.
Yep, thank you.
So for questions, would it be like satisfactory to just say, so like if you just did row reductions, for example, and you end up just saying, oh, there's not a pivot in every row, or there is a pivot or in every row, so
Yeah,
on and
that's
so
enough.
forth.
Yeah.
Therefore, okay.
Mm-hmm. So, I mean, yeah, pivots are also, this is a way of proving things, right? I mean, the sort of, ultimately, a lot of our proofs boil down to some statement about pivots.
Yeah. Okay.
And that's that's a really concrete way of proving something.
Okay. And then once we get to that point, we don't have to like say theorem number or whatever, right? Okay, great. Okay, thank you.
Yep.
Professor, is there going to be homework due next Tuesday?
That is a great question. I guess not, since there was no homework assigned this week.
Okay, thank you.
About the definition of uniqueness, shall we use the textbook's version of exactly one solution or the lecture version of at most one solution?
The textbook version, yeah. So as I mentioned in the announcement, we are now sticking with the textbook version definition of uniqueness.
Okay. Then for the review page, you write pivots in every row or column as criteria for existence and uniqueness.
Yeah.
So these statements should be applied for coefficient matrix.
Yeah, these
right?
should be, you're right. These should be applied to the row echelon form of the coefficient matrix, to
Okay.
REF of A, or row
Alright.
of REF of A.
Mhm. Okay, thank
Good
you.
question.
Is another way to think about the true and false example that we did in class just now? Can we think about the matrix, the A matrix, and then say that there has to be a pivot in every column, and then therefore the transformation or the span of the transformation would have to equal RM?
You could try that. My sense is it might be harder, but you could try that. So yeah, one important point is the solutions, because there's so many interconnections, the solutions are not unique. Every problem has, many, many different ways of solving it. So you could try that. Some are easier than others. My sense is that doing this with pivots might be a little harder, but in principle, there might be a way to do it.
Okay, thank you.
Yep.
If we're trying to use something like use a connection between two ideas that we proved in class, and the question isn't specifically like asking us to prove that, then do we need to show proof for it, or can we just say like we know this, so we know this, and like
Yeah,
we
just
proved that
state
in
it. Like, for
class?
example, you can say this transformation is onto because this is its standard matrix, and this is the row echelon form of the matrix, and it has a pivot in every row.
Okay, good. Thank you.
You don't have to prove why those equivalences are true. Again, unless I ask you to specifically. Any other?
Yeah, so if we kind of heed your advice and write down all the relevant definitions, do you want those in our work or like in the actual proof, or
Oh,
should
no,
that
no, no,
be?
no. Unless I ask you to, no, this is for your own problem solving ability. This is for
Right.
own problem solving process. You don't have to write the definitions in the answer unless I ask you to.
Is there any harm in doing that, or do you
No
and
harm,
the
no
graders
harm.
not want to see that?
No harm. We don't mind.
All right. Thank you.
Yep. In fact, it's usually if somebody does that, it's extremely clear that what their thought process is, so we don't mind.
If your little map of like connections between different types of objects really like makes sense for us, can we put it on our study sheet, or do you want us to actually make our own definition?
I would at least like you to write it by yourself.
Okay, okay. Yeah.
Like, don't just take a screenshot of mine. Yeah, but yeah.
Okay, good. Thank you.
A quick question. So when it comes to write down a cheat sheet, can we write on a tablet, or does it have to be like on paper?
You can write it on a tablet, but it should be handwritten in
Okay.
your handwriting.
All right.
This is really random, but since you're uploading these on YouTube, could you save the chat as well and upload that the way you did with lecture 1?
I can upload the chat on B courses. I don't know how to upload it on YouTube actually.
Okay.
I mean, do you? Or
no, sorry. I just saw that it was uploaded for lecture 1, so I thought.
Okay, I'll just lecture 1 was live streamed on YouTube, which is a little different.
Okay.
This one I'll just post on B courses. Yeah.
Okay, thank you.